Okay, hello everyone. So today we'll talk about the probabilistic graphical model on text compression. And let's start with our introduction. So what is probabilistic graphical model? So why we construct a model? So what is a model? A model is a compact and modular representation of a complex system, and it has the ability to execute complex reasoning patterns like a Latin space of something. And another thing about models is it is able to make prediction, not just prediction but estimation as well. And another thing is that it is able to generalize from particular problems. So the particular problem that we are facing now is text compression. So yeah, this is why we're trying to construct a model to solve a particular problem. And one of the problems is that we're trying to find probability of words by. We know that probability of words by and POs are correlated, but most words like tiger and basketball are independent. So probabilistic model for which a graph actually has a conditional dependence structure between random variables. So yeah, so PGM is a way to express the conditional dependence between different random variables. And next thing we're going to talk about is the nodes of a PGM represent the random variable or states, which is in this diagram we see that A, B, D, and C represent the random variable and states. For example, probability of A, B, C, and D can be represented as probability of A times probability of B times probability of C and D given A and B. So which is represented in this graph. So given the graph structure, we are actually able to model the joint distribution of a complex joint distribution instead of building a whole table just for the joint distribution, which takes a lot of computational space and so on. So next, we're going to point out is that the missing arcs represents the conditional independent assumption. So if there's no arcs between two nodes, that means they are independent, and the graph structure implies the decomposition. Okay. So next, we'll talk about the objective, which is to compress English articles. And what is the strategy? So the strategy is to use the PGM. PGM is a model, where model is a kind of information extraction method. But the things that using PGM, we usually do lossy compression because we are unable to memorize the whole text and apply it. Yeah, we are unable to memorize the whole text. So in order to use a lossless compression method, PGM can't do the task because it's a probability distribution, so it will lose some information. So what we do is that we take in other kind of methods. So to overcome this problem, we also use PGM as a probability predictor, which sort of learn the distribution of the text in the distribution of words in the whole text. And the next thing is we're going to introduce the arithmetic encoder block, which is learned in class, where it is helpful in lossless compression. So PGM helps us to learn the probability distribution, and arithmetic encoder encodes the text. So this is the whole architecture. And next one, we introduce the encoder and decoder framework. So for the encoder framework, we start with a uniform distribution, as seen in the first. It's shown on the top. So we start with a uniform distribution, throw in the arithmetic encoder, and then given the text, we encode the text. After encoding, we put it in the neural network predictor. Using the neural network predictor, we can actually learn the distribution of text, and using a recurrent neural architecture, we can actually proceed with the next encoding part. So using neural network, we can keep encoding the next text, and using the new probability distribution, we can encode the text and so on. And using the S2, the new input text sequence, we can keep encoding. And in the end, we have the solid representation of the overall text, which is a good way to learn the distribution of text. And using this method, we are actually able to obtain the compressed sequence as shown in the right. So as for the decoder part, it is the symmetric of the encoder part. So given the compressed sequence, we jump into arithmetic decoder. And in the beginning, we knew that we have the uniform distribution, use uniform distribution, and we can get the original text, which is S1. And using S1, we can throw it into the neural network predictor, which is the symmetric of the neural network predictor that we use for the encoding part. So using the neural network predictor, we can use arithmetic decoder to decode the S2 text, and so on. We can retrieve the whole text. So this is overall framework. Parameters and B is the bias. And the input of model will be the k previous symbol, and the output will be the multinomial distribution of the next character. So we can represent it as follows. No. Okay, so 1 second. Okay, so for the probability predictor block, we have the fully connected dense model, which is a combination of multiple fully connected layers defined as H, where is equals to the sigma, where sigma is the iteration function, X is the input matrix, W is the weight matrix, plus the bias. And the input of the model would be the previous K symbols, and output would be the multinomial distribution of the next character, which is defined as follows. And the cardinality of S is defined here, which is the alphabet size of the sequence. So, and this is obtained by adding a softmax layer at the end, which is defined as follows. So the softmax tries to turn the output into a probability distribution. And another method is use the LSTM, long short-term memory, or a GRU single layer, a GRU single output framework. So LSTM or GRU belongs to the class of gated recurrent neural networks and have been used very effectively in the past few years for various natural language processing applications. And for every symbol SR, the input consists of the past K symbols SR minus K up to SR minus 1. So each of the symbols is an input to a bidirectional GRU cell. And finally, a softmax layer is applied on the final hidden state obtained from the LSTM GRU cell to turn the output into the probability distribution. And a bidirectional variant of the GRU is used, which is denoted as bi GRU, bi GRU. And next is the architecture of the LSTM cell. The LSTM predictor framework, where it consists of multiple cells, cell 1, cell 2, up to cell k, where each cell takes the previous k text as an input. So cell number 1 takes the previous k text, cell number 2 previous k minus 1 text, and so on up to the previous text. And the output of the last cell is passed to a softmax and a dense layer. So this is what we call a single output framework. And the next is on the multiple output framework. So one problem is that the LSTM GRU single output framework suffers from rendition gradient issue, which makes the dependence on further symbols weak. And to alleviate this issue, LSTM based framework, which includes the explicit dependence on past K symbols where fully connected layers on top of the LSTM embedding is considered. We will show a diagram describing this part on the next slide. So an input consisting of K symbols, which are fed into K LSTM cells, which is the same on the single output framework. And the LSTM cell output are concatenated, followed by a dense layer and a subsequent softmax layer, which give a final probability distribution to be used for arithmetic encoding. Okay, so this is architecture where we use. So the one below is the same. So we have K LSTM cell, which takes K inputs, the K previous inputs. So the difference is that on the output of the LSTM cell, we use all of the outputs and concatenate it into a large array and pass it through a dense layer, two dense layers. So a dense layer with ReLU and another dense layer with softmax output, where we get a probability distribution of the next text sequence. Okay, so then we start training on the text we have, which is given in the Lovecraft website. So the batch size is chosen to be 64. The sequence is divided into overlapping segments of length k plus 1 and shifted by 1, where the first k symbols in each segment from each input from the input and the last symbols act as the output. So an Adam optimizer is used as the optimizer to minimize the categorical cross entropy, where default parameters and the batch size fixed at 1024 is used. So okay, and the model is optimized for a maximum of 19 epochs, which the training is terminated early, and if significant improvement is not observed. For area epoch, the training data is shuffled, sharp in upstream convergence. The models after the area epoch if there is a decrease in average loss from previous minima. In the LCM or GRU-based model, CUDNN accelerated implementation is used, which reduces the training time by approximately 7 times. So the authors attempt to overfit the training data because we only have the training data and try to compress the training data and use the weights learned from training data to decompress the data. So the goal is to overfit on the training data. So as mentioned, the proposed framework stores the model weights as part of the compressed representation, and the train model is used only for prediction on the training data. Okay. So next is the arithmetic coder block. So an entropy coding technique is used to compress a stream of data given a probability estimate for every symbol, condition, and pass. And as taught in class, the arithmetic coding maintains a range in the interval of 0 to 1, and every stream of symbols uniquely determines a range. And the range can be computed sequentially and is directly based on the conditional probability distribution of the next symbol. And at the end, the range is encoded in the bits, forming the compressed data. And the decoder performs the inverse operation given the probability estimates. Okay. And this is the results using the deep compression method. And we choose 8 tags from the Lovecraft website, and as shown is the compressed files, and everything is good except the second one as a top, where I'm not sure why the size increased, but yeah, we try to look into the problem, but yeah, as time is a factor, so we just give up, and yeah, this is the results. And our competing team has not released the results yet, so we can't compare with them. And this is our presentation, and this is the reference. This is the paper that we use for our implementation. Okay, thank you.